Alright, our topic today is going to be using linear equations. So our big ideas today are statistics and probability, investigating patterns of association in bivariate data, using equations of linear models for that bivariate data, and then interpreting the slope and intercept in the linear models. So our related topics, as you can see, there's a couple of 8th grade standards in the middle of the screen. Our standard is 8 SPA3, but all of those standards have to do with bivariate data and the relationship between those two variables. And our standard is a specific prerequisite to that top right high school standard that leads to interpreting data. So our interpretation of slope and intercept is an essential aspect of our standard. So our standard is to use the equation of a linear model to solve problems in the context of bivariate measurement data, interpreting the slope and intercept. So breakdown of those essential words right there. Bivariate measurement data is data on each of two variables where each value of one of the variables is paired with a value of the other variable. So you can see in our image we have temperature and ice cream sales, and we're looking at the relationship of how those two variables interact with each other. In this image, it seems that as temperature gets bigger, ice cream sales gets bigger. Equation of a linear model. So these equations attempt to model the relationship between two variables by fitting a linear equation to observed data. So our formula for this one is y equals a plus bx. And you can see in the picture to the right a couple of lines with their specific formulas sitting on top of them, so you can see what that looks like. So x would be the explanatory variable, y is the dependent variable, b is the slope, and a is the y-intercept. We'll break down slope and y-intercept in the next slides. So slope describes the direction and steepness of a line. So our equation for this is y1 minus y2 all over x1 minus x2. So as you can see in the image to the right, if the slope is positive, the line slants up. As x gets bigger, so does y. So that would be a positive slope, and that's the same as a positive association because it's a positive association between the two variables. And so and vice versa is true for negative slope and negative association. And finally, the intercept refers to the y-intercept, which is the point where the line crosses over the y-axis. If you can look at our picture here, you can see that x would be 0 in that case, because that is the point of the y-axis. So a typical task. The scatter plot and regression line show the average income in dollars in several major American cities plotted against the rent for a 222-bedroom apartment in those cities. The fitted line has a slope of 0.031. What is the best interpretation of this slope? Choose one answer. Alright, go ahead and pause the video and take a minute to find your answer. Alright, so the answer for this one would be A. On average, each $1 increase in average income was associated with a 0.031 increase in average rent. So in this case, they gave us a slope of 0.031. Since they only gave us one number, you can assume that 1 is the denominator. So 0.031 over 1. Now remember, rise over run. So the rise is 0.031. That means the rent goes up 0.031. And the run, it was 1 from our 0.031 over 1. And that means that our x variable is increasing by 1, which would be an average income increase of $1. For our challenge task, we have the scatter plot shows the relationship between the number of airports in a state and the population of that state according to the 2010 census. Each dot represents a single state. So part 1, how would you characterize the relationship between the number of airports in a state and the state's population? Go ahead and pause. So the variables are positively associated. States with higher populations tend to have more airports. If you look at our graph, you can see that the line is trending upward. As you increase the x variable population, so does the y variable of number of airports. So that is a positive association. So part 2. Latoya uses the function y equals 1.35 times 10 to the negative 6 all times x plus 6.1 to model the relationship between the number of airports y and the population in a state x. How many airports does Latoya's model predict for a state with a population of 30 million people? So go ahead and pause the video. So you're going to start with this equation, y equals 1.35 times 10 to the negative 6 power, all times x plus 6.1. And all we're going to do is take that population that they gave us of 30 million, and we're going to substitute it for x. So you're simply going to plug it in and work out the math, and you'll see that with 30 million people, we would predict 46.6 airports. And finally, part 3. What does the number 6.1 that appears in Latoya's function mean in the context of airports versus populations? So remember, the equation was y equals 1.35 times 10 to the negative 6 power, all times x plus 6.1. So go ahead and pause. The model predicts 6.1 airports in a state with no people. So remember, our y-intercept would be when x equals 0. So if x was 0, then the model would predict 6.1 because that would be the only variable unaffected by x equaling 0. That 1.35 times 10 to the negative 6 power would become 0, and 6.1 would be the numbers of airports we would have regardless of no population.